So, in this document we will be focusing on the bag of words feature extraction and TF-IDF feature extraction again, but this time it will be on malware dataset, which is like a little bit different than the text data we saw earlier. This is like the byte values. So, we will be forming n-grams and do TF-IDF analysis on specific bytes specified in the documents. So, to get an idea what is included in the homework, you can open the lesson 2 lab. So, in that there is 2 tasks actually. In task 1 we will be focusing on the bag of words feature extraction and using n-grams, and in the second task we will be focusing on using the TF-IDF feature extraction. So, basically there are 2 tasks specified in the document. So, task 1 is defined in task 1.py, correspondingly task 2 is defined in task 2.py. You need 2 other key important folders and files, that is data sample that contains the data. We will be focusing on the .bytes file. If you open one of them, as professor shown already, this is the bytes specified in the memory, and you will read this portion of the file to do your feature extraction part. These are the actual bytes and these are the memory addresses specified in hexadecimal format. So, and you also have a train levels.csv file. So, as you will be able to see, there are some kind of ID associated with the type of malware it is. So, inside data sample, if you see, the file names are something like arbitrary string, which are actually the ID for the corresponding files, and you will have corresponding labels for that file in here. For example, if you try to sign, this is the file. So, this file will have the label specified. This is the corresponding files label for the type of the malware data it is. So, just let me make sure that everybody was able to download and set up the system. So, this time to run the programs you will be needing some command line arguments. So, to run the program you have the commands listed in the readme.txt file. For example, if you want to run the task1.py, you have to type this command python task1.py, provide the training folder where the data are stored, like the data sample folder, and the corresponding labels file where the file listing the labels for each instance. So, you can open a terminal here on the bottom of the PyCharm IDE and just copy and paste it there to run the task1.py. So, running the program will require a little bit of time because it is going through large files to process the bytes. In the meantime, while the program is running, we will focus on what is being done inside the task1.py. So, basically I request you to go to the bottom of the task1.py and see how it works actually. So, basically in the first line inside the main portion of the code, we are calling the extract n-grams method, which will extract n-grams specified like it will extract for us the 1 gram, which is like kind of bag of words straightforward, and the bigrams. So inside extract n-grams, we will first formulate some parser and set up the arguments we passed in through the command line. Then we read labels from the specified label file, which is train_labels.csv. Inside the read labels method, if you go there, read labels basically reads the file and store the class labels as a Python dictionary, like ID maps to the corresponding label. Then we will focus on the read files method, which is actually reading the files from the folder specified in the command line argument, and it also takes the dictionary that is been generated by read labels method. Inside the read files from the training folder, we will be considering only the files that has a bytes in his file name. As I have already shown, we will be considering only these files, these dot bytes, these dot bytes. The other files are not required for this program. Once you open the file, we have a helper method to load it as a byte array. So you will provide the file name. This method will give you a byte array representation of the entire file in sequence. Then with that byte array, you can start building the n-grams. Now here build n-grams takes two arguments, the original raw byte array that will be used to build the n-grams, and the n, the value of the end, how many consecutive bytes you want to be as a unit for your feature. So here n equals to 1 means each byte becomes one feature. Similarly, in the next call, when you see the n equals to 2, it means that every 2 bytes becomes your one feature. So my program has completed running, so I'll explain what the output means in a minute. So let's focus on the build n-grams method first. Basically, we first initialize a counter to keep track of how many times a byte is appearing in a file, particular file. First, we clean up the byte array if there is any unwanted, there is none value. This is just like filtering the values. Then we have the byte array something like this. Say byte value 76, 85, 39, 65, 101, 128. This is our byte array. So basically, what we will do for certain amount of certain number of n, we will consider that byte and keep it inside the counter, that how many times this 76 occurred. Counter 76 should be 1 now. But when you are considering the bigrams, then you consider 76 and 85 as a whole. It becomes your unit, and inside the counter you will store something like this: 76, 85. This is your bigram. It is now 1. Then for bigram, you remove the window by 1 and just follow the similar procedure. Now basically when we build our n-grams, it gives us a kind of this mapping. Counter 76 becomes 1, but for our method we use from scikit-learn, it wants a vector. So we build it. We build the vector like this. We know the size of the vector will be 257 because byte value can contain 256 unique values, and 257th one is for a marker. So whenever you have a counter 76 equals to 1, at some point of time in the array there is a index 76. You keep that counter value to 1. Then for suppose example counter 65 was 7. Then suppose this is one is the 65th indexed, and you put it 7 here. So now it becomes a vector that we will use for our classification for our feature extraction algorithm from scikit-learn. So you will see that after extracting n-grams, we call it the convert to vector method that does this mapping. And we get our byte 1 grams in a vector format. Similarly, we get byte 2 grams, but we don't convert it to vector because that is very sparse. And it works in a similar manner as we have explained for build n-grams. Then we just return those values to the main method as we called it in the extract n-grams earlier, and we print the values that byte 1 grams and byte 2 grams. So in this small example, we have basically 93 instances to work on. At the bottom of your output, you will be able to see that the length of byte 1 grams, that means this many 1 gram vector you have, and 1 gram vector represents 1 instance. Similarly, for byte 2 grams, you will get another 93 vectors, and there are 93 train labels because you have 93 instances for those. And when you go for the value, see there are, if you focus on this pair only, it's a kind of it's a tuple where it means that 222 and 52 as byte values appeared only once throughout the document. 142, 54 as a pair of bytes happened 2 times. 142, 58 again as a byte of pair happened 2 times, and these are the records. So you are basically seeing the bigram output of the. I think it is the IDE has limitation like how much output it shows, but for 1 gram it should be something like this. Sorry, it should be something like this. 76 happened 7 times. 89 as a byte value happened 14 times, something like that. So in a kind of like you are calculating the term frequency as a pair, something like that. So let me know if you have any issue on this part, then we'll advance to the next one, where in addition to this, we'll do the TF-IDF calculation. So we'll be continuing to task 2 if. So for the task 1, we have actually extracted the bag of n grams, and we also extracted bag of 1 grams, which is basically the bag of words or bag of bytes in this scenario. So in this one, we will extend that feature extracted feature vector to TF-IDF. It works similarly as before, but inside main method you will call extract TF-IDF method now, and inside the extract TF-IDF method you again parse the argument that has been passed through the command line. You again read the labels from the file here, and inside read files this time you will do the same thing. You again extract the bag of 1 grams and bag of 2 grams along with the labels. In addition to that, using the vector that you have generated with 1 gram, you will do the TF-IDF calculation. So, inside byte 1 grams there are list of vectors that represents each instances. With when you have all the instances in a vector represented form, you can derive the TF-IDF from there. Actually we are using some pre-built library. Again we are using the TF-IDF transformer that we have used before, and we hand over the vectors that we extracted using the extract TF inside the extract TF-IDF method, and we return the TF-IDF2 array. So, this time the output should look similar, but I mean it should like it should be scores. I mean it will not be an integer, not a frequency count anymore. It will be a like natural decimal point numbers. So, and here we will be printing the TF-IDF along with the train labels. So, let us run the program and see if it works. Oh, no, I cannot run it this way. So, let us open a Python terminal, clean it up first, and use the command specified in the readme.txt file, that is again similar to task 1 python task2.py. You specify the folder name for training and the labels file. Again it will take some time to complete the task. To clarify a little bit more, basically when you are saying that we are taking bigrams and 1 grams, for 1 grams we are considering like this 56, this is 1 gram, this 8D is a 1 gram, this 44 is a 1 gram, all are specified in hexadecimal number. So, but for when you are saying that we are considering bigram, then we are actually considering 56 and 8D together, 8D 44 together, and then we are calculating our